So, with a short course about information-based complexity, Erich Novak, so you're welcome.
Thank you very much, and welcome everybody. So I want to give a short presentation, a short introduction to information-based complexity. What kind of problems do we discuss, and what kind of answers do we obtain? So let me start. So this is the first lecture. There will be a second lecture, and the plan for today is just to explain what kind of problems do we investigate, and I will present an example for C infinity functions, for very smooth functions, and I will tell you what is tractability and what is, so to speak, the opposite, the curse of dimension. And so the question is, can we get this tractability properties by smoothness properties? And so the general answer will be no. No. So even if you have a very smooth inputs, you do not have tractability, and so we need additional structure of our problems, and this is what I discuss a little later. So this randomization is here in small phase because it will not be discussed today, so it will be part of the next lecture. Okay. So we always have problems for functions. So we want to compute integrals, for example, or we want to compute the function itself. We want to give a reconstruction of the function. So we want to approximate the function. And the idea is the function is only given by function values. So we do not work with, I mean, it is really not about symbolic computation. So it is like we assume you have a subroutine, an oracle for function values, or possibly for Fourier coefficients, something like this. And the question is, how many of those function values do we need to compute the solution? So to compute the integral or to compute the maximum of the function f. So this means we have incomplete information, and because of this we will have an error. We will have an error epsilon, and then the question is, how many function values do we need to get an error epsilon? So it is here again, how many values, how many function values do we need to compute this, what I call the solution operator, so this what we want to compute, this S of f, up to an error epsilon. And it really does not make sense to ask this question for a single function, so we always have to, so to speak, we need a whole function class, and we need to solve the problem for the whole function class, because I mean for a single function f, this output is possibly just a number or so, so it does not make sense to ask how much time do we need to compute this number. And it is a little, for me it is a little embarrassing, but because it's so trivial, but I think it should be very clear from the beginning that all kind of complexity questions only make sense if you somehow define a class f of functions. So the question is, how many function values do we need to compute S of f for all elements from the class f up to some error epsilon. And this is what we call the information complexity. This is the information complexity, and this is how somehow the whole field gets its name, information-based complexity. So we are interested in such a number, and of course we have to prove upper bounds. We have to prove good upper bounds for just one algorithm, for example, to have an upper bound of this number n, but the lower bounds should hold for all algorithms, of course, because I mean, here the question is how many values do we need, and of course the idea is to use the optimal algorithm, and how many function values does the optimal algorithm need to compute what has to be computed. So I want to start with a very simple example, and I mean just to set the stage maybe. So we do optimization for Lipschitz functions, and the functions are functions in one variable. So this is the class of functions, and we want to compute the maximum of f. And then it's not difficult to show that if you take equidistant points, then this is optimal, and so the optimal function values are these function values, and then the true maximum can be in this interval. So assume that you have always got the function value 0, then the maximum could be 0, of course, or it could be, it could be 1 divided by 2n, and so the optimal algorithm or an optimal algorithm would be given by this, and we really can compute in this very simple example this information complexity. So it's of this form. And of course, it's easy to see there's not a better algorithm. So this is very elementary, and you can do exactly the same thing in several dimensions. So now we have this class of functions. So again, Lipschitz function depends on d variables. And again, we want to compute the maximum. And again, one can prove, now it's a little more difficult to prove, if n is of this particular form, then the optimal xi form a grid, and we get more or less the same optimal algorithm. But now, of course, we have m and n. So n is, in my talk, n is always the number of function values, the number of functionals. D is always the dimension. And now, if we express the error 1 divided by 4m, like in the first example, if we express it in n, then we get this formula. So, and now you see the number of function values is really exponential in the dimension t. So we have the curse of dimension. So this is a case where one can prove this curse of dimension in a very simple way. So the computing time increases exponentially with the dimension. And how should we think about this example? So one way to think about this example is that probably this class F is extremely large. So this contains all Lipschitz functions, and so there is no smoothness involved, and so probably this class is really much too large, and we should somehow ask what would happen for smaller classes of functions. So this is what we want to do next. And now we consider CK functions. We take as F, we take a unit ball in CK, and K times differentiable functions. And now it is very much well known that the optimal order of convergence for optimal methods is of the form n to the minus k divided by d. And I mean, this is really a very old result, more than 50 years old, and people like Bachwalow proved such results, and so this is quite well known. So this means in terms of the complexity is of this form here. And this sign here means it is just the order of convergence. So there are constants involved, and these constants depend on d and k. But the order of convergence is given by this. And now, of course, we can have different combinations of k and d. And for example, we could have the case where k is large compared to d, and then this order of convergence is nice. So if k is 2 times d, for example, we have a nice order of convergence that does not depend on the dimension. And now, of course, I mean, does it mean that the problem is easy? And traditional studies in numerical analysis, they just concentrate on the order of convergence, and they probably would say if the order of convergence is fine, then the problem is fine. So I want to discuss the extreme case. K is infinity. Then we have a very small class of analytic functions, and the order of convergence is great, it's just excellent. And what will happen with the complexity? Okay, so here is my class of functions. So we have the infinity functions, and all derivatives are bounded by 1. All derivatives are bounded by 1. So this class is quite small. We have a very good order of convergence. So the order of convergence is better than n to the minus k for any k. And so, I mean, this is expressed here. The order of convergence is better than n to the minus r for any r. So the order of convergence is quite nice. And I guess in most textbooks about numerical analysis, the guy would conclude the problem is somehow easy. The problem is somehow easy to solve, because the order of convergence is great.
Erich, solution iterator is maximum of the function like it was? Or?
Yes. I mean, I just used here this problem of maximum, but actually you could also use the approximation problem in the L infinity norm. It is more or less the same, up to a factor 2. So actually the proof is even for the approximation problem. I believe I prepared this for a lecture for optimization people. So I mean, I stay for a while, I stay with this problem, but you could also use S of f is f, and here the error is in the infinity norm. So somehow it is easier to formulate this problem because the output is just a number, and then it is clear what the error is. So the error is just the difference between real numbers. Okay. So what will happen with this problem? So again, the order of convergence is excellent, and so the result is that we do not get tractability for this problem, but first maybe I write down a few notions of tractability. So just in general, what we consider is information complexity. So the number of function values depends on epsilon and d. And somehow the best result what we could have is that we have such a polynomial kind of convergence, but the order does not depend on the dimension, and also the constant does not depend on the dimension. So this is what we call strongly polynomially tractable.
It's positive.
Excuse me?
P is positive.
P is positive, yes. I mean, the meaning is if there exists a positive P and a positive C with this property, then we call the problem strongly polynomially tractable. And polynomially tractable, we allow also a polynomial dependence on D, but as you see here, only a polynomial dependence, not an exponential dependence. And we call the problem weakly tractable if this equation holds, and this basically means that it is not exponential in D or in 1 divided by epsilon. Okay, now the result for the problem which I just mentioned. So again, I mean, we have this this class of the infinity functions, and we deal with the optimization problem with computation of the maximum, and for this problem we have the curse of dimension. So if we want to obtain an error smaller than 1/2, then we need exponentially many function values. And so to speak, the initial error, the trivial algorithm, if you output just 0, then of course you do not have to compute anything from your function, and this algorithm has an error 1. So because there are functions in the class with a maximum 1. So this trivial algorithm would have an error 1, and and I guess any reasonable algorithm should increase this trivial algorithm at least a little, so by a factor of 2, and if you want to achieve this, you need exponentially many function values, at least 2 to the power d half. So the information complexity is quite large. So I want to prove this result because the proof is really simple. So we have now two different norms. We have this norm f in the space. So this norm is the sub of all infinity norms of derivatives, and we have the infinity norm of the function itself. And this here is the unit ball of L infinity, and how looks the unit ball of the F space? It looks like this. It is much smaller. But there are some functions that have the same norm in F and in L infinity. And for us, it is important to have many such functions. So we need whole vector spaces of such functions. And let's start with the case d equal 1. Do you know a vector space of functions with this property that the two norms are equal? There is not really such a space. I mean, there's only the space of constant functions. So this is a little not good. Constant function. On the interval 0, 1. Oh, but maybe you have in mind a different kind of functions. You have in mind maybe the functions sine and cosine. So they have this property of the derivatives are getting not larger and larger and so. So they are a good example, but not, I mean, they are a good example, but not a very good example, because it is only okay if the interval has the length pi. So here we still consider functions on the unit cube. So you could have such a thing with dimension 2, like f of x is a sine x plus b cosine x. And can you increase, no, I mean, can you decrease the size of the interval? You can decrease a little. You can take the interval from -1 to 1 and take functions f of x is a plus bx. So this is really somehow the starting point. If you consider linear functions on an interval of a length at least 2, then you have this property. But of course, it is just a vector space of dimension 2, and moreover, we would prefer this kind of domain. And so this is how it works. We take all functions, all polynomials of this form. This is a vector space of dimension 2 to the s. And s is basically half of D. And all these numbers here are 0 or 1. 0 or 1. So these are, in each direction, they are linear functions. And so we have the dimension increases, of course, exponentially with the dimension d. And now it looks much different. So now we have for this space, how is it called? Vt. Now, if I only consider the space Vt, then the two norms coincide. And the dimension is the dimension of Vt is n plus 1. And if you have any information with cardinality n, so like this, so what can we say about the kernel of such a mapping? So the kernel, because of this dimension smaller than this, it looks like this. So the kernel is at least one-dimensional, and f is 0. And this means in this space Vt, and this means, of course, also in the space f, we have a function with information 0 and with maximum 1. This function has maximum 1. And of course, we cannot distinguish this function from the 0 function. And so we have two different results. So we have s, I mean, maybe I put a tilde. We have s of tilde is equal 1, and s of 0 is 0. But of course, our algorithm cannot distinguish between the two. So this means an of 0 will be an of f tilde. And I mean, whatever this algorithm outputs, you have at least for one of the two functions you have a big error, and so this is what is claimed. So the error is at least 1/2.
And so in the examples, what happens when x is larger than p for cosine and sine? Why is it that?
Excuse me, say it again.
Example, you took sine and cosine basis only on 0p, and what happens when they are larger than p? What's the problem?
If it's smaller than p,
Larger.
Yeah, the problem is that if you now shrink, or that you'll have an extra multiplier, which will be the ratio between the lengths of these intervals raised to the exponent d.
But I can take a cosine on the whole line, it's so usually not greater than 1.
no, but my functions are only defined on the unit cube. And if you I mean, somehow the extreme case is like if you have this interval from, and you take here the sine function, and if you now decrease the interval a little, only a little, then the maximum of this, the norm of the function itself, the subnorm of the function itself, will be smaller than the subnorm of the derivative. because the derivative has norm 1 and the function itself has a little smaller norm. So this means this example can only be used if the interval is large enough. And of course, if you have a larger interval, you find more and more such functions. But as I said, for d equal 1, you really find only the constant functions if you insist on such a small interval.
The norms of all derivatives are the same. What is the point?
I mean, the norm of the derivatives, by norm I mean the norm of the derivative on the given interval, of course. And so to have this property for a whole space of functions, it is a very special property, and so this is used for the proof of this for this lower bound. So, and this is somehow the principle, we call it the principle of incomplete information. So you get for two quite different functions, you get the same information, and this is why your algorithm must be quite wrong, at least for one of the two functions. Okay, and I mean, in a way it means some of our colleagues said that this class is a little artificial because this class is so small. I mean, who wants to deal with such a small class of functions where we have such a strong properties about derivatives? But of course, somehow the point here is to prove lower bounds. And of course, the lower bounds, of course, are even stronger if the class is very small. So if you agree that this is a very small class, then of course it is clear that the lower bounds also hold for the larger classes. So in a way, this means that smoothness is not a good property to prove good upper bounds. We need more properties about the structure. Okay, maybe just a remark. So if we take the same class of functions, and if we consider the problem of numerical integration, then we still do not know whether for the problem of numerical integration we also have the curse of dimension or not. So this is an open problem for many years now, and several colleagues studied this problem, and it is known if we decrease this class even a little more. So for example, if we not only take derivatives in the direction of the axis, but also in the direction of any direction, then we have better results, we have positive results, we have no curse of dimension. And on the other hand, if we have a little larger classes like this one, for example, we could take a very large number k, 2000, k is 2000, but fixed, and we study this class, then we still have the problem of dimension, also the curse of dimension, also for the integration problem. Okay, now I want to to define some different kinds of structures that you can assume, and then you get positive tractability results. And so the first kind of structure is what some people in optimization call partially separable functions, and this means that you have a function f depending on d variables, and this d can be quite large, can be very large, but this function can be written as a sum of functions that only depend on k variables. So we have a function of this kind. And quite often in physics we really have such kind of a structure, because, I mean, think about Coulomb potential, for example. So you have many particles, but the potential is given as a sum of functions that depend, for example, only on 6 variables, 3 coordinates from one point and 3 more coordinates from the second point. And as a rule, all these problems of integration and approximation are tractable if you assume such a property. So, I mean, here, I mean, k is fixed and d is quite large. And it was studied by different colleagues, this kind of structure. So, another kind of structure was defined for so-called weighted norms. So we have weights to define the norms, and it turned out, so I mean, much of this research started like 20 years ago, or even a little more than 20 years ago, when people noticed that with some kind of quasi-Monte Carlo methods you can solve quite high-dimensional problems, and it was not really clear why one could solve these problems, so a kind of a theory was needed, and the functions that they had in finance, for example, had a special structure in the sense that some coordinates were much more important than other coordinates. So we have not, like, I mean, in finance they often had 360 dimensions, but not all dimensions had the same influence on the function, and not all groups of variables were equally important. And so the idea was to define norms like this. So here we take the derivative, we take always only the first derivative. So it is a first derivative in any direction which is an element from U, and U is a subset of D. So we take partial first derivatives in several directions, and this is the norm, and this L2 norm here is multiplied with some constant, and this is the definition of the norm. And you see, if this gamma weight is quite small, then, so to speak, this gets punished. You get here a large number, and this means to be in the unit ball of the Hilbert space means that this integral has to be small. So we can model quite many different properties of functions and of physical models or of models from economics by different kinds of weights. So, so U is a subset of this set, and these are non-negative numbers which are needed to define the norm. And for example, I mean, so to speak, the classical case would be if we have all equal weights equal to 1, and then in this case here we consider L2 approximation, and so this L2 approximation has different tractability properties depending on whether which weights we consider, and also whether we allow only function values, lambda standard as the function values, or whether we allow all kinds of Fourier coefficients and weighted integrals and so on. So for equal weights, the problem is weakly tractable for lambda all, but we have the curse of dimension, and we have this curse of dimension even if we only want to compute the integral. And for finite order weights, what does it mean, finite order weights? It means that the weight is 0 whenever the cardinality of the subset U is larger than K. Then the problem is always polynomially tractable even for lambda standard. Okay, so I mean, when this kind of study was started in '98, usually this kind of product weights were studied, so where we have really a different importance of the different coordinates, and later more general weights were also studied. So again, we can model different properties of functions by suitable weights. And so what are the main results? So maybe I should stress this paper of Ian Sloan and Henryk Wozniakowski. This really studied the whole field of results, and this was the first paper and was cited hundreds of times, and so this was somehow the beginning of all this stuff. And by now we have, for many spaces and many different weights, we can characterize really what does it mean to have strong polynomial tractability, to have polynomially tractable problems, to have weak tractability, and so on. And so, of course, if the weights, if these gammas are very small, then it is maybe easier to get tractability results. And maybe as a remark also, for the upper bounds, of course you need algorithms. You have to define algorithms, and the first proofs, also the first proof in this paper, were not of a constructive form. So it was, the authors used the probabilistic method, so they computed some averages, some expectations over the worst case error of a whole family of algorithms. And of course, this is not what you would like to have as a programmer. So you would really want to have your good algorithm in your hand. So this was only the starting point, but later, in many cases, the authors or other authors from Belgium, from Australia, found constructions of such tractable algorithms. Okay, yet another structure I would like to discuss such functions of this form, so they are called rank 1 tensors. So the function f can be written really as a product of one-dimensional functions. And so f is really given by t one-dimensional functions. And the assumption is that these factors have a small infinity norm, and also the rth derivative is somehow small. And so this is somehow the new class of functions, and what can we expect? And I should really mention the first paper by Bachmeier, Dahmen, Devor, and Krasitik. And they proved, and it is maybe also clear that one can prove such a result. The order is the optimal order of convergence of algorithms is n to the minus k for all d and what is the different constant m. So again, the order of convergence is fine. It does not depend on the dimension d, and it is also somehow maybe obvious because you have functions of one variable, you have d such functions, and of course it is enough to know the d functions of one variable, then you can recover the whole function f. But still, this is really not the whole truth, and because in some cases we have the curse of dimension, and in other cases we do not have the curse of dimension. And it is interesting that there is exactly one point, and this point is this m. So if m is too large, then we get the curse of dimension, and if m is only a little smaller, then there is a deterministic algorithm with polynomial complexity. So we proved this first only for randomized algorithms, but later on David Krieg and Daniel Rudolph found a deterministic algorithm to prove this statement. And maybe I give you one idea. So if you know one function value, one single function value, which is different from 0, then by this property here, you can simply recover the one-dimensional functions on these coordinates, and then it is really just a one-dimensional problem. So it is really like what you learn in your first lectures about numerical analysis. However, maybe it takes a long time to find such a value which is different from 0. So it could be that f of x is 0 in large parts of the cube, and then you have a problem, and so this means you really have to find such a value where the function is different from 0. Okay. So what I wanted to to say today is just I wanted to give some definitions and a little description of what we are doing in IPC. And so the claim is if you have standard spaces like such CK spaces and high dimensions, then you cannot expect to get algorithms for such problems like integration or optimization or so. And so the remedies are you somehow you need an additional structure in your problems, and a different kind of remedy would be to allow randomized algorithms to study Monte Carlo methods. And I mean, it is mainly done to compute integrals or expectations, but it can be also done for L-infinity approximations. So there are also interesting recent results. But this is really in small print because it was not part of this lecture today. Thank you very much. Any questions?
Hello, take the guidance, yeah.
Okay, questions? I have a question. But what about rank K tensors? K is fixed. Is the same?
No, the same. Not. It will be much more difficult. And
Yeah, sure.
I know some people started to study this problem, but I'm not so sure. I think there are no published results.
I don't know. This is
No.
Yeah, I know. I remember when we discussed this issue with those authors, and they were kind of, not clear. I mean, certainly their proof cannot be generalized for that case directly.
I mean, what they had an algorithm, and this algorithm had a super exponential cost, and for every epsilon and for every m. So it was really, they did not have a distinction between easy cases and difficult cases. So, I mean, they had only this order of convergence.
Other questions?
Maybe concerning the last result, this exact value of 2 to the power of r and r factorial, what is the example? The previous slide.
Yeah.
This one.
It means for this n greater or equal than 2 to the r factorial.
I mean, the problem is to construct a function which has a large L-infinity norm, and in addition also a large part of the domain where the function is 0. So somehow an extreme case is like this. The function is 0 here, and so we have, so to speak, we have many such functions. We have 2 to the power d such functions. For every quadrant we have such a function, and the function could now grow to some large number like 1. So here is 0, here is 1, and this can only happen if this constant m is large enough.
Other questions? If there is no more questions, let's thank the speaker again.